Okay, we're going to get started for today with the third and final keynote of Mohamed Daoudi. He is a full professor of computer science at IMT Nord Europe and the head of image group at CRISTAL Laboratory. His research interests include computer vision, machine learning, human behavior understanding. He has published over 150 papers in some of the most distinguished scientific journals and international conferences. He is or was the associate editor of Image Vision Computing, IEEE Transactions on Multimedia, IEEE Transactions on Affective Computing, and Computer Vision and Image Understanding, Computer and Graphics. He's also the guest editor for Computer Vision and Image and Understanding for special issues on Eyes on People, Recent Trends on Human Analysis, Perception, and Generation. Also guest editor for Image and Vision Computing on Learning on Manifolds, Learning with Manifolds and Computer Vision and Sensors, Computer Vision and Human Analysis from Face and Body to Close. Many guest editor spots. IEEE T-Biome for Selected Best Works at FG in 2019. He was the chair of FG in 2000, the general chair of FG in 2019. It was in Lille, France. And then chair of 3D Object Retrieval Symposium, Shape Modeling International Conference. He's organized successful workshops in face and gesture analysis for Health Informatics, learning with few or without annotated face, body, and gesture data, generation of human face and body behavior towards a complete analysis of people from face and body clothes, Manifold Learning from Euclid to Riemann. He has served as area chair of 3DV 2021, IEEE FG2024, ACM Multimedia on 21 through 24, UPISCO, and he will serve as the general chair for FG next year. He's a fellow of the International Association for Pattern Recognition, a senior member of the IEEE, and a member of the ACM. That is quite a list of achievements.
Thank you very much.
Please take it away.
Thank you very much. Thank you very much for this presentation. So thank you for your coming here, because I think some of you now are sleeping. I'm going to explain and to share with you some of research that we obtained in my group. So about 3D face and body imagination. And a very few words about the motivation about this word. I think you are familiar with the 3D face or face and body. So the question is why 3D human generation, 3D face generation, or 4D face generation, imagination. There are many applications of this in many fields, like social robotics to interact with robot, and virtual reality also. So and the last thing is one thing very interesting in my group is maybe this is a photo of me in my lab. We have seen this kind of system, motion capture system, and it's very expensive. It's very expensive, and one idea is maybe with this human body generation or 3D face generation, we can maybe save money, instead of using this kind of system which is very expensive, and also time to generate human body motion 3D face generation. So this is some of motivation of this work. And in this talk, I'm going to, there are two parts in this talk. I'm going to share with you some of our paper. The first one is more about 4D face generation, and the second part, it's maybe it would be about human motion generation. This is two parts of my talk. So I'm going to explain what we obtain and what we did recently. So the first work, or first thing that I'm going to explain is how the idea of generation of 3D face generation or 4D face generation. And there are very interesting questions that when we would like to, given some 3D face, like neutral face here, we would like to generate some 4D face or 3D face sequence of 3D face, given some neutral face. So, and given some neutral face, given some facial expression, we would like to generate a dynamic of some 3D sequence of facial expression. So there are some interesting questions. It's how can we model the motion of 3D face, and how can we synthesize a sequence of facial meshes, but with by preserving, but we have to preserve also the identity. This is very important now criteria here. So given some neutral face with some identity here, we would like to generate some sequence of 3D face by preserving the identity of neutral face. This is some question that I am going to, to give some a part of the solution of this this problem. So our framework is based on two parts. The first one, it's the first part of this framework is what we call 3D motion, again. And the second part, it's a neural network which able to reconstruct 3D face based on some landmarks. So in this framework, the idea of this framework is given some neutral face, we would like, and given some expression, label here, expression, we would like to generate a sequence of landmarks. So to give you a big picture about this landmark, the picture of this framework, so there are two parts. The first one, it is the first part of this work, it is how to generate a sequence of landmarks. So here we assume that we have the landmark, 3D landmarks for each 3D face. So the idea here is we separate between two information. The first information is the motion, which will be based on the sequence of landmarks, and the second part is the geometry of the face. So, in the first part of the network, which we call 3D motion GAN, what we are going to do is to generate or to learn the distribution of the sequence of landmarks. This is the first part. The second part here, given the sequence of landmarks that we are going to generate, we are going to, to compute like a dance or a deformation of the face. So given some sequence of landmarks, we would like to reconstruct or to decode or to reconstruct, a sequence of a dance of 3D face. And given this, we can use this neutral face, neutral mesh here, by adding this deformation, when we can obtain a sequence of 3D face. And we have defined some cost function. So I'm going to explain maybe in more detail what we do here, and the main idea that we have proposed in this work. So as I explained, that we assume that we have a sequence of landmarks, 3D landmarks, and we would like to learn the distribution of this sequence of landmarks. So the first thing that we do here, what we did here, is we suppose that we have the sequence of landmarks, and we can, each frame of these landmarks can be seen as a vector. With some here, I don't remember exactly, but we have 68 landmarks. It means that we have a vector with the size 68 multiplied by 3, because we are 3D, each landmark here is in 3D coordinate. So we have a vector. So a sequence of landmarks could be seen as a sequence of a vector. And it could be seen also as a curve in some space. So this is a curve here. So a sequence landmark, not now, it is like a curve or trajectory of this vector. So this is the first thing, that we represent each sequence of landmarks as a trajectory, as curve. And there are several now in the literature, there are several ways to represent a curve. And here we use a very nice representation called the square velocity or root velocity function to represent each curve. So the landmarks, sequence of landmarks is a trajectory, it's like a curve, and we represent each trajectory here as a representation. The name is Q here. It is based on a derivative of the trajectory. It is there are many now theoretical motivation of using of this representation. So and one thing is if we normalize the curve, so we have a curve. If we normalize the curve to 1, for example here to 1, the modulo of this representation Q is equal to 1, which means that Q here now, when you normalize the curve, Q is living in some sphere. So this is very nice representation because each sequence of trajectory is represented by a curve, and each curve is represented by one point in sphere. So all the information now is in one point in this hypersphere. So, and this is, there is also nice properties of this representation is we are able to recover, the curve. So given this representation Q, we can obtain, the curve, the original curve. So this is the representation of the sequence of our trajectory, of our landmarks. So this is very important here because I am going to use the representation. So from now, each sequence of landmarks is represented by one only a compact representation. The name is Q here, represented by this formula here. So, and now we would like to learn this representation. We would like to learn this, the sequence of trajectory. Okay? So, to learn a distribution of, given some facile expression, we would like to learn this sequence of trajectory. So, the goal here is to build like this generator here, which is going to learn the distribution of the sequence of trajectory. But in this case here, there is some challenge. The challenge is, as I explained in my previous slide, each curve or each trajectory here, sequence of trajectory here, is represented by one point in the sphere. And we would like to use this again, to generate this kind of expression of facile expression based on landmarks. But as you know, GAN is a good candidate for Euclidean data. So we have to extend this idea of GAN to non-Euclidean data because here Q is living in sphere. This is what we did here. We define a new GAN where each we have the data here. It's not in Euclidean space but in sphere, and we define this new generative model which is able to generate expression or a sequence of landmarks based on this representation Q. So we defined different kind of loss function, here. But the idea, this is the main idea here, that we have like a classical GAN, we have a generator here, we have discriminator here. The only thing that we have to be careful here is that our data here is not living in Euclidean space, but in sphere. This is what is defined here, and when we finish the training, we are able to use the generator now to generate a sequence of facile expression. And the second part of this framework is, given this sequence of landmarks that we are able to generate with our motion 3D GAN, we can now, what we do, we have a sequence of landmarks. We compute, the difference between each frame of this landmark, and this is like a sparse representation of this displacement. But we would like to, what we would like to do is, given this sequence of displacement, we would like to have like a dense displacement. And this is what we do here. This is a new neural network here, based on what we call spiral convolution, because here we are going to reconstruct or to decode, the information from a sparse representation to some dense representation. This is what we obtain here. And we have now a sequence of deformation of the face that we are going to add to neutral face to obtain a sequence of deformation of the 3D face. And once we have this, we define here a loss function to compare the sequence of this 3D face here with the ground truth, and to define this neural network. This is two parts. The first part is to generate landmarks, and the second part is to define the sequence of deformation that we are going to add to neutral face. And with this, as I explained, that we have to be careful to be sure that we preserve the identity. And with this, we preserve the identity of 3D face because we add to this deformation, a small deformation to a neutral face. This is what we have done here. And I can show you here very quickly some results that we obtain. The first thing is we have to evaluate the reconstruction of 3D face. And what we do here, we compare the reconstruction of based on our approach of 3D face. When we compare this, we show that our approach provides a good result, and when we compare to state of the art, so we have a good reconstruction here. I can show here. If we reconstruct more than 80% of, between 90% of vertices, we obtain less or lower than 1 millimeter. And the second part, it's not enough because to have, good reconstruction, it's good, very important, but it's not enough. We have also to be sure that the landmark sequence that we generate with our generator provide a good facial expression. So we have to evaluate the facial expression. If we generate a good facial expression with our generator, this is what we do here. And when we compare the landmarks generated by our network, we obtain the accuracy of when we try to compare or to classify the facial expression, we obtain a good result also here when we compare to state of the art. This is what we obtain. It's a quantitative result, and we have here, I can show you here some results that we obtain. This is some example of facial expression obtained with our framework, and this is what we have here. And one thing interesting with this framework is the ability now to interpolate between two sequences. Given one sequence of 3D face, another sequence here, we are able to interpolate between them because this is because our framework, as I explained to you, that each sequence of landmarks, it is represented by one point in sphere, and you have another point in sphere represented by sequence of landmarks. We can interpolate between them. This is not complicated. This is very classical formula. We have in sphere, we can copy geodesic paths to go from one point to another point, and this is what we can obtain here. This is one example here of interpolation. So given the source here, this is the source, what we have here, this is a target here, and we can interpolate between two sequences to go from one, the source, to target. Okay, and this is interesting to generate a new 3D face. The second thing is with this framework we can transfer speech from one source to face here to another one. To different identities here. So we have this source face here. We can transfer the movement of the face of the lip from the source here to this face here. So this is what we obtain with this framework. But there are some limitations. The length of the sequence is limited to 30 frames. This is one limitation of this, and we have only one transition from neutral to apex, expression. And this is we extend this work. I'm not explaining to you here in more detail, but we extend this work to take into account all this information. And there is another limitation that we have to start with neutral phase. And what we do, we extend all this work to start with not necessarily with neutral phase, and to work and to have more than 30 frames, and to have more than one transition. This is what we did in this paper in our affective computing this year. This is an extension of this work. So I'm going to now to share with you another work that we did. This is the first work that, given 3D neutral phase, we are able to generate 3D facial expression 4D. And but there is another limitation. This is very important limitation in many techniques in 3D phase, because there are a main difference between 3D phase or 3D in general and 2D. There is no what we call a parameterization, global parameterization. In 2D you have an image. There is some order. In 3D there is no order. There is no order in the points. So this is a very big challenge in 3D. When you move from 2D to 3D, it's not easy. You have many things that you have to revisit or to take into account. And this is a very quick thing that brief, maybe for some of you who are not familiar with 3D. In 3D phase representation, there are two kinds of representation. The first point cloud, we have only 3D point in 3D space. And we can also have like a connection between this 3D phase to have what we call a mesh, triangulation mesh. And we have vertices, we have edge, we have face. And we have no order, which we call parameterization. And this is what we try to do recently, since now my 2 years, yeah, to revisit many methods, to take into account the fact that we don't have, when we scan, we don't have the same parameterization or the same order. We have some, yeah, this is some very important. And one thing that we start with is what we call a decoder. The encoder, auto-encoder. The auto-encoder is very well known now. I think many of you have use this kind of autoencoder. There are two parts. We have the encoder. We encode some information like here, Euclidean information X. We have the encoder. We have latent space. We have the decoder, and we decode. And the goal here is that the output of the decoder should be very, very similar to the input here. This is what we, this is something very well known. Okay. The question is, how can we extend this kind of encoder not to 3D information? And so this is main challenge, because we don't have, compared to image, the data is very hard to collect. And the mesh, or the triangle mesh, is not vector space. It's not Euclidean space. So otherwise, if you want to have some like Euclidean space, you have to make some order. Why not? But we have to make some more pre-processing, like a point correspondence, all these things. What we would like to do here is to learn or to encode the 3D phase in some latent space, because it's more easier to work in latent space because it's Euclidean space than in some nonlinear space. Okay. So this is what we do here. Our autoencoders are what we would like to do is to have some criteria. Our first criteria to have robust to remeshing. It means that if we have X1, X2 with some different meshes, but correspond to the same phase, we would like that our encoder, our latent space, the vector, should be very similar. And this is another thing that we would like to do, is to train our encoder with a varying mesh topology. I mean that this is, there are autoencoders in 3D phase, but they assume that they have the same topology. Here we would like to do something we scan, and we have, maybe we can have the different data set, database, with different meshes topology, and our autoencoder should be able to learn these meshes. This is what we do here. So to do that, the general method that we propose here is, there are two things. The first one is the decoder. The decoder will compute the deformation field, not construct now the face, but 3D face, but deformation field that we are going to add to the template, what we call the template. And we have the encoder that I will explain to you, that should be robust to the variation of topology. And the last thing that we propose here, a new loss function. This is some idea here. Our encoder is, the big picture of our encoder is this. We have two parts, the encoder and decoder. And what I just explained that we would like that our decoder here will decode deformation field, not the face, but deformation field, that we are going to add some template. We deform the template, and once we deform the place, we will compare this template deformation added to this template to the input here, the face, with some loss function. Okay? But what happened? Which kind of encoder, which kind of decoder can be used here? So this is a very important question, because there are few neural network on 3D which have some, robust to variation of the meshes. So for the encoder, what we propose here is to use what you call point nets. A point that's a deep learning network on a mesh, and it has some nice property that it cannot work on mesh, but in point cloud. And this is what we do here. So the input here, it is not the mesh, but a point cloud. But so we can, with this point net, we are able to encode some latent space. And for the decoder here, this is another neural network which we call spiral net, which has a very nice property, but it can work only with a fixed topology. But for us, it's not a problem, because what we would like that to decode deformation with spiral net, and we added this deformation to some neutral face here, some template face here. And once we added this template, the deformation here, we can compare between the output here of our spiral net to the input here. But we can use a very classical, loss function like this one. You compare vertices by vertices. But the problem is that what we would like is to train with more general data set. It means that it could be that the output here of the formation here, the mesh, should be different from the mesh of the input. So we cannot use this kind of loss function here, because we don't have this correspondence between points. So what we propose here, a new loss function to encode, to compare between this output here of decoder here and the input by using what we call varifold, representation of the surface. So if you are interested by this representation, there are now many paper on this. But the idea is the main property of this varifold representation in surface is that if you have a continuous surface, it is invariant to reparametrization. But if in our case, it's discrete, because we have only point or the mesh. In this case, it's robust to reparametrization of the surface. And this is a good candidate for us, this kind of loss function, because in our case, we don't have the same topology or the same representation of the surface. And this is what we do. And the varifold in this case of in the mesh, it's based on three information. The first information, in each triangle here, we have the center of the triangle, we have the normal, and you have the area of this triangle. Based on these three information here, we define a matrix that can be used to compare between this kind of meshes. And this is what you obtain here. I can show you here. So when we encode, we encode each mesh or 3D face in latent space, which is Euclidean space. It's more easier now to work in latent space than in the space of 3D face. So this is what we do here, for example, for interpolation. So given one source here, we encode this, one source here. This is another, the target here. So we are in Euclidean space. We can use this kind of formula to compute the path, to go from the source to target here. And this is the deformation here to go from this source to this target here. And this is another example here and here. I can show you some maybe more deformation. So we are able now to interpolate between two 3D face based in this latent space. And we can encode 3D face. We have one Z, which is in Euclidean space. And we can interpolate between two faces based on a very simple formula. And this is this is interpolation. We can also, in latent space, because we are in Euclidean space, we can do some arithmetic operation here. For example, we can subtract this face, another face, add another face, and we can neutralize this face to obtain a new faces here. This is something that we can do, which is very complicated to do in the space of the surface, but here we can do it. And the last here, it's sorry. This is another example that I would like to show here. That, as I told you, that we can now, because our network is robust to reparametrization of. If we change, the point of topology of the surface. We are able now to encode this surface in some latent space. We can add or subtract 3D face with different meshing. This is very important property that in our network. This is something that we do, so we are able to do this kind of operation based on this. So this is the second work that I show you here. It's we are able now to interpolate, to generate a new 3D face or new sequence of 3D face based on this interpolation. And the last part about this work on 3D face is in the first work and the second work, there is no external information. There is only neutral face. We generate 4D. In this work here, what we are going to do is to add some new information like audio. So given some 3D neutral face, and with the face here, it's very important. This is a very big challenge here. It is arbitrary topology. I scan 3D. I have a scanner. I scan 3D face. I would like to generate, given some audio, I would like to generate 3D face with this audio, but with different topology, not the same topology. And so this is what we do here, which we call this scan talk here. So given a neutral face with different topology or mesh, okay, this is what we do. So in this framework, we have two parts. The first part is what you call the encoder, and the second part, the decoder. So for the encoder here, for encoder given neutral face, and to learn or to train this encoder here, we have the audio and we have 3D face. So as I explained, we would like to work with different kind of topology. So one candidate is .NET that I just explained to you in my previous work, but it cannot work here because we have some. We would like to have some more local information or some about faces, which we cannot do it with the .NET. So in this case here, there are not many candidates, for training 3D face and which are robust to the changing of parameterization or remeshing or topology. And diffusion-net is one of them. It's very interesting in our network. We have some good properties with deep learning on surface. And we can extract some local information because it's based on what we call Laplacian on surface. It's local information. And they have some good properties like invariance to isometry or some group transformation. And we can compute some local information. This is what we do here. So given some 3D face, we can compute two information. The first information from 3D face, we have in each vertices here, we can compute some scalar, some vector, which are some good properties like robustness to topology and to some which is geometrical operations. And the second part is the audio. So we have the audio here, which is here we use very classical, encoder. It is Huber encoder. So we have this information of face. We added this information to audio here, and now we have the decoder, which decode this information given a vector, which two information, geometric information and audio information. The decoder here is able to decode this information based in diffusion net, okay, and we obtain a deformation. We have a sequence of deformation with decoder, and we add this deformation to our face, the face that we have. At this, we have now a sequence of a new sequence of 3D face, and we compare this with the ground truth with this very simple loss function here, because here we have the same topology. There is no problem to use this kind of loss function. So this is what we do in this work. So with decoder, we have a deformation. We added deformation to the 3D face that we have as input, and you have a new sequence of deformation that we compare with the ground truth. And this is what we obtain. This is one interesting thing is that during the training instead of there are some there are some methods that do something similar to this or work, but they assume that they have the same topology. In our case, it's not the case. We have the training. We train our network with different kind of data sets. This is VOCA, BIWI, multiphase. They don't have the same topology. Okay. And we have some metric evaluation like LIP, because LIP plays a very important role, when we would like to synchronize the audio to face. And there are some other criteria here. So this is one example that I can show you here. This is 3D face. This is
the stale smell of old beer lingers.
Yeah.
It takes heat to bring out the odor. A cold dip restores health and zest. A salt pickle tastes fine with ham.
Okay, and this is now what we can do with our framework.
The stale smell of old beer lingers. It takes heat to bring out the odor. A cold dip restores health and zest. A salt pickle tastes fine with ham. Tacos al pastor are my favorite. A zestful food is the hot cross bun.
And this is another example that we have many examples that I should
ScanTalk is able to generate plausible animations on face meshes with very different geometries.
Yeah. This is what we got with this, we obtained with this framework. So one advantage of this framework is we're able to train with different kind of meshes, and we can...
ScanTalk is...
And we have also some quantitative result we obtain. We compare with different methods, and we are competitive. If we compare with state of the art, we are very competitive, but with the advantage that the fact that we are able to train with the different kind of meshes of the face. So this is the first part of the work. So I'm going this 3D phase, and I would like now to move to another work. So as I explained in my presentation, that I have two parts: human 3D face generation and human interaction generation. I will explain why interaction is very important here. So the goal of human motion generation is, to generate natural, realistic, and diverse human motion. So this is what the main goal of this. With some challenge, the human motion is non-linear, articulated. Okay. Human motion serves as non-verbal communication. If you generate some human motion, you have to take into account this kind of criteria. And human motion generation include also some external information like context, audio, environment. So this is the main challenge. I'm not going to solve all this challenge in this talk, but this is some, that we'd like to do. So why it's very hard, human motion. Human motion, the body has about 600 muscles, 200 bones, and many joints. So it's very complicated to analyze all this information. But usually what we do, we work only on surface of some landmarks. Okay, to analyze this human motion. Not now, we cannot take into account all this to analyze all these muscles or the bones. So we are going to to work on surface or on landmarks. This is what we can do. There are some different kind of motion data that can be used in this case, what we call key point or 3D landmarks, and also rotation based. So our work is based on this key point. But this is this kind of information that I'm going to use in this paper, in this work. So we have a sequence of landmarks or sequence of key points, 3D point. This is sequence, and this is some other example. This is based on capture this information on by using like a Kinect, and this is we capture the information based on motion capture. Okay, this is this information that I'm going. But I would like to tell you that there is also simple, which is very, very popular in our representation of 3D human. But I'm not, it's not. I'm going to use the 3D coordinate. Okay. So in human motion, if I can summarize, the idea of human motion that we. This is the state of the art this year. We have. The condition, we can have text, audio, also the environment. We can have, there are different kind of generative models, like a GAN, diffusion model, and we have a motion. Okay, so, but I'm going to focus more on interaction, but I would like to give you some idea about what. So this is the state of the art. As you can see here in this slide, there are more and more works on this and publication on this. I see that in 2000, in this year, last year, there are more and more publication on this, and they use different kind of human motion. This is based on text, audio, music, all these things. So, but all this work here focus more on single human motion. But in this work, something new. We would like to work more in human interaction, human motion generation, not single human motion, but human interaction generation. Why? Because I explained that there are many applications of this to interact with the robot. We can do it also in our case in my lab. We're more interested by this kind of interaction with the avatar. There are many applications of this kind of interaction. So there are few works, but there is the last work. I think I just give you this. This is there are few works on this topic, and this is maybe one of the last work on this, Romos. There are some comparison also with our. They compare also this work with our approach here. So this is human. I will start with human reaction generation. So the idea here is, given some action, we have action of some human. We would like to react or to generate the reaction of this. So this is what we would like to do here with some challenge that we have no additional information. We don't have action label. We don't nothing. We don't have like a prompt text. We don't have audio. We have only action. I would like to generate the reaction of this. This is what we would like to do. I think there are very few work on this. I think this is maybe this work it's similar to what we did, but there are few works on this topic because I think this is there are many challenges on this kind of reaction to generation to action, and we would like to have some coherence between action and reaction. This is what we do. So I can show you very quickly what we do here. We have what we do. We have our is based on transformers here. There are two parts. The first part is what we call motion encoder. So given some action, we encode the motion in some latent vector here. We have it's based on the idea of transformer. We have self-attention, self-spatial attention between the 3D coordinate, and we have also a temporal attention between a sequence of landmarks or point. Yeah. And the second part, it is decoder. So given the action sequence here, we encode in some latent vector here the sequence of the action, and we have the reaction here. We do the same things. We have the same thing, but in our decoder here, what we do, we added some information about what we call the distance between the action of the two persons. We have landmarks. We know that sometimes there are some distance that play more important role than some other distance. So we take into account what we call interaction distance between the two persons. And this is what we do here. We decode this information. We obtain a new some reaction to generate a sequence here that we compare with the ground truth here. And the cost function is very simple. Cost function here, we compare only the distance between landmarks. Very simple cost function to compute here. And we have this this framework here, which is given some action here. We are able to generate reaction to some action here. And this is some result that we obtain here when we compare with some state-of-the-art method. So given the blue, it's the input action. And for example, in our case, it's a red one. It's the reaction to the action. And this is another example here. So the input is the action, and you have the reaction here. I think these preliminary results here are not bad. I think it's good, and promise, result here that we obtain. And this is, in the dance, it's more complicated because dance is very complicated. It's complex, interaction between two persons here. What we do, this is due dance. So we try to do something, what we call long generation sequence. It's more complicated because it's more than, I think, 2 minutes here. But, that what we do is we are not able to regenerate 2 minutes. It's too long. I don't remember exactly. Maybe it's maybe not more than maybe 10 seconds or something like this. And we have something like we generate some subsequence, and we have next one conditioning by the previous one, etc., etc. So this is that can. But what we observe is that in the end we accumulate the error, and it becomes not the generation is not so good. So this is some limitation of this work now. And we have also some evaluate this by using some metrics like FVD, it's Fréchet video distance, which the idea here is to compute, the distance between two distribution our generator, what we generate, and distribution between the ground truth. And we have also classification accuracy, diversity score. It's important to have this kind of and when we compare, we compare with different kind of action here, and we have several, data set. We obtain some competitive result on different kind of data sets. Okay. And for diversity also, we have a good result, except I think here in this data set here, but. It means that this first approach, it's not maybe the best one, but this first approach to this human reaction, generation to action, provide, I think, a good result here. I would like to finish with this. Now this is reaction to action, but now we are also more and more interested by generation of action, human interaction. Not only reaction to action, but we would like to generate. So the idea here is given some label, class label, or some prompt text. We would like to generate action, like here, for example, cheers or drink, and we can generate this kind of action. Okay, this is what we propose here. Oops. So this is what we propose in this work here. Is the main challenge is the high quality of the motion, interaction generation, and also high diversity. Because when you generate this kind of human interaction, we would like also have some diversity of generation. So this is based on diffusion model that we propose here to extend this idea to diffusion model. I think provide a very good result in image and video, and we extend this idea to human interaction generation, 3D human interaction generation. So diffusion model is based on two processes. The first one, it is what we call forward diffusion process. This is no training, no learning here parameters. We added some noise and image. This is some noise, and we have the reverse denoising. This in this part we have to learn the noise. This is the main idea of this. I will explain what we do. So if you compare to maybe it's one we can explain the good result obtained by diffusion model, because maybe if you compare to variation encoder or GAN, maybe variation encoder or GAN, generate sample in one step, because we have latent vectors and we decode. We have some sample here, but diffusion model we have different step. This is maybe one advantage of diffusion model. Yeah, we have some noisy example here. We remove some noise. Another step, we remove some noise, given some network here, and in the end we have obtain some the image or video. So this is maybe one advantage of this. So this is what we propose here. So exactly the same framework as diffusion model. So I am not going to explain here all the mathematics or probability here behind this model. But what we do here, it is given some here what this is the formula, the cost function used in generally now in diffusion model here, given some human interaction here, seconds of human interaction here, 3D here, here. We added some noise of this. And given some, this is the formula of diffusion model. We multiply this by some quantity here. We obtain some noisy here. And what we would like is to estimate or to predict what we call the noise, okay? By using some network. Usually they use a UNet or something to do that. But here we propose a new network to do the noise, this sequence here. So, and this is what you obtain here. We have this formula here. This is loss function. And now we have to define this network here. So our network here, it is what we call a graph interaction transformers. Here we take into account the interaction based on the graph. We have like a very special graph. It's not a full graph between all the landmarks or the points in 3D points, but it's a very special graph. We have a graph between the interaction between two persons. And this is what you call bipartite graph. And we have something similar to transformers. We have text here. This is what I explained, that here we have a text or prompt here. And we have here the two seconds. We have seconds, the first seconds here, the second seconds here. And we define some, transformer self-attention between the frames, and also here. And here we have a cross attention here because we have text. Here we use clip to do this. I have a clip here. But we have to take into account the interaction, and we define here, it is here, we have like latent space here, like vector here, we have another one here, and we define like with the same, here we have the same size as here, the length here, n. And we define this bipartite graph to take into account the interaction between two persons, and we can now define, to predict, this error, epsilon, that we have to remove to obtain a new image, a new sequence of 3D. This is what you obtain here. This is our framework. So we go from some noisy, like 3D in 3D. Step by step, we have our transformers here. We remove some noise. We have the second part, etc. We obtain the last a new sequence of human interaction. And this is this part here to go from here to here. What we do, this is what we do here. Exactly what we do. We have the noisy, 3D point here. We have our framework, bipartite graph, interaction transformer that we define. And we have two information. We have the class label of the prompt. We have time, of course. And we have, as you can see here, we are able to predict with our framework network here, this noisy here. We remove all this part here from this to obtain a new sequence here that we have here. This is exactly what we do here. So to go from here to here, what we do this computation, okay? And this is, in the end, we obtain this framework. We have all this part. We have the forward process. We added some noise, and we have the reverse process, and we define this, to remove the noise. we define this bipartite graph interaction transformer to remove the noise from this from each sequence. And what we obtain this kind of that it's okay. Okay, oops. We obtain this kind of this is a bipartite graph. This is ours here. So we can generate this kind of human interaction between two persons here, and we have also this kind of in NTU and Dance. We are able to generate this kind of interaction between two persons. For I think Dance, yes, Dance. I don't remember exactly. I don't have the name here. But I think the name is Ramba. I don't know why we don't have in the screen. We asked to dance Ramba, yes. And this is what we obtained. This is ground truth, and this is our approach that we are now able to generate. The dance between the interaction between two persons. For a very long sequence, it's okay, but as I explained that maybe we have to work more on this. This is some limitation. We cannot, I think my PhD student try to do some, I think 2 minutes of generation, but what we observe is that we accumulate the error in the end. We have something which is not very good. This is maybe one thing that we have to do. So this is, and of course, there are some, we compare and we have some qualitative results that we, by using some criteria like FVD, multimodality, etc. There are some classical criteria that can be used to evaluate, human generation or in general, human interaction generation. And this is, I think when you compare, we have some we have a promised result that we obtain here. And we ask also, we did what we call user study. This is, I don't know if you agree with this, but we do this because one reviewer, asked us to do that. So we ask, we have like a forum, and you ask the users to some question about which skeleton sequence is more realistic, which skeleton sequence match the inputs better. Text, okay, text, we have a text, and better. We ask users, and it seems that what we obtain with our method, the users are happy with what we obtain with our approach. This is, I don't know, but this is something that that we can do. So I would like to finish with this. It's at the end of my presentation, and what I would like to what we're trying to do now is now modeling more complex interaction between person or between actors, and also the interaction between human and object or environment. This is something that we're interested by this kind of, to generate, human body, but with interaction with the object. And in this talk, I give you some result on reaction generation to action. But I think we can also do something very. There is, I think, some challenge on this. Maybe this year it's ACM Multimedia, this challenge about faster reaction generation in dyadic interaction, and the same idea is given some phase, and how can we generate expression given some expression, okay, and this is open question. I'm not sure if it's, I don't know. This is something that we're thinking about it. Because in human interaction, what we call a synchrony, it's very important. When I smile, usually you smile. This is what we simplify my definition of synchrony. But in human, when we generate human interaction, we would like to take into account this kind of something very well known in psychology, what you call synchrony, during the interaction between human body or maybe also and facial reaction. This is some idea that I think. That we can combine face and human body generation. And thank you very much. Of course, it's not only my work, it's the work of many of my colleagues in the world. So this is some example of my PhD student and collaborator, in different,
Do you have a question, Conf? Do we have a mic? That was excellent.
Thank you very much for the presentation. Co-articulation is very important, right? So when you generate a sequence of lip movements, when you generate, let's say, 30 frames per second, that's about a second. So do you have any thoughts on, let's say, if you want to produce longer sequences, right? How are you going to take into consideration the temporal dynamics of speech, and how will you model co-articulation?
You mean how you take into account the long sequence in this?
Yes. So if I understood correctly, right, your model, right, will process 30 frames per second, right, the short seconds. But if you want to generate, let's say, a longer sequence, you will have to take into consideration the co-articulations things.
With audio, or because in the first work, as I explained, that in our first work we don't take into account this, but we have another work that we try to do something to take into account this kind of during the speech or facial expression. To take into account different transition, this is in our paper that I don't explain here, in the last paper that we did. If you want, I can show you this paper. But we have something, we do some.
Can I ask another question? Yeah, okay.
Yeah, please.
The second question is about metrics, right? Metrics. Usually, my experience on this type of work is that objective evaluations are very different from subjective evaluations.
Yes.
Have you find metrics that match well with perceptual evaluation? Things that, for example, mean square error is a problem in my experience, because it tends to reduce the range of behaviors, right, to sort of the mean, and so you don't see the whole spectrum of movements.
I agree with you. It's why in the last work, in all these works, what we did, we asked some users, subjective, and we gave them this, the audio and the animation of based on this audio, and we asked them some questions. And we have criteria, I think it's very classical criteria that we propose to compare and to analyze, this subjective. So in all this work, we did this. We asked the users, subjective, study, to ask the user what they, with some questions that we have to define some questions. I don't know if it's good or not. We have some questions, and we ask them what they think about the animation, what they think about, we have text, we have audio, and we have animation, if it's okay. We have this kind of, we did this, yeah.
I also had some questions.
Thank you very much. So very impressive work, very difficult problems. I have a question about the 3D face, the models that you're using. When you're dealing with key points, some key points are structurally stable, but the contour key points depend a lot on the pose. How do you deal with that? Because all the images we've seen were frontal, but what happens when the...
Yeah, this is one limitation, and I agree with you. This is what we would like to do also, to take into account. Yeah, I agree with you. That's what limitation of this work. All this work here, we assume that it's in front of, there is no, And this is what, for the generation, there is no here, all generation will have, generate facial expression, all this, but there is no generation of the pose. I don't know if there is, so we have to, in the future. This is one limitation of this work is this, So maybe we have to think more about this. I agree with you. This is a very good, future direction.
Thank you for the talk. And a couple of questions. And in terms of the diffusion model you have used, because there's the degree of the noise in terms of you want a diffusion procedure, right? So are you learning any different degree of the noise in order to control the unit to adapt to diffuse and also denoising.
Here we don't use unit. We use our,
Yeah.
we propose a new network, to denoise,
Yeah.
to play to denoise. So what is your question? How to
Identify and learn the degree of the noise? Because you do not want to denoise too much or denoise too less, right?
Yes.
Otherwise, to create too artificial like the noise, right?
Okay. I understand.
Is that something you've thought about?
I cannot answer to your question. Maybe I have to be more sure about this, to answer to your question.
Yeah.
Because I don't know if about the noise, how can we define this kind of...
Yeah.
Yeah, I agree with you. This is something that...
This comes another very challenging problem, because if you handle the 3D mesh, right? So now the mesh is very clean. But what if we have the scan with lots of the outliers? Does that will handle this one?
To be sure that we are talking about the same thing.
Yeah.
Here there is no noisy, the mesh diffusion net. It's
exactly.
in 3D environment, like John said, okay?
Yeah.
For the mesh, it's very difficult. It's more. I think there is. I see,
right.
There is 1 or 2 papers on this.
Yeah.
There are few works because it's very difficult.
Yeah.
I think there is one work from Imperial College just published this recently. I'm not sure if published or in archive, but there is. But because it's very challenging problem, how to the noisy diffusion model on 3D and the mesh. It's,
right.
This is, I think, open question.
So are you considering anything like, for example, similar idea with the code former? You have a low quality version, you have a high quality version, right? You pair this low and high as a training, create the code book, right?
Yeah, good, yeah.
Then this time you can also learn from low to high. And at the same time, so you transfer to another model to create another generative one.
Yeah,
there's something like this one, right?
Yeah, good suggestion. Yeah, this is yeah.
Because right now there's lots of the nerve model, right? Create the nerve head. Anything you thought about the comparison or evaluation on that part?
Yeah. No, I agree with you. This is a good suggestion or a good thing to the future, about diffusion model or 3D images. Yeah, this is something that we are thinking also in my group. I don't know.
We
don't have yet just on this.
Yeah, we can talk about more about this one. Yeah, it's very interesting work.
Yeah, this is very interesting.
Yeah, and also regarding the measurement of this data, right?
Yeah, I agree.
You didn't consider any volumetric.
The
array, right? Because they can project in the different directions.
Yeah.
And also the geodesic measurement is not also considered, right? Because that's part is with another measurement.
Yeah, I think that's a very nice, good direction in the future for,
Yeah, thank you very much. Very, very nice talk. I appreciate it.
So, hi, Mohamed. So I have a few questions, but I will find you afterwards. I'd like to start with my question. First of all, it's a very great talk, and I've been aware of some of your works, but I learned a lot today. And my question is about, in your first work, where you model motion trajectories in this sphere, as a point in a sphere, right, in a manifold. Have you considered doing the same thing when you do, for example, reaction generation? Because there also you have some key points and you have a sequence of key points, but you had a different encoder. Is there a reason for that?
You mean if we can make connection between
space,
the trajectory and
yes.
space? Yeah. This is we have another paper, but we did something similar to this for in FG. Maybe last year or 2 years ago. And by using this idea of the trajectory for the prediction of human motion. So given some human motion, I would like to predict the future. And we use exactly the same idea. So we extend this idea of trajectory and this nonlinear space for this. So I agree with you that maybe this is good idea that in this work maybe we can also apply this idea to But we did it for human motion prediction.
Okay.
Yeah.
Great.
Yeah.
And
this is the second question.
What?
You have some other questions?
Yeah, but if we have time or.
Yes.
So my next question was about, at the end of decoder, first you predict the deformations and
yes.
then you add it to the template.
Yes.
Is there a reason why you didn't try to directly predict the results?
Yeah, because for to preserve the identity, maybe you can lose the identity. Here we are we have only deformation. I think it's much better to predict deformation than to predict the 3D face, because you can lose this and it's more complete. I think with deformation it's much better. Otherwise you can lose the identity of. You don't preserve the identity. We did something similar to this, but with this we have deformation added to the face, so we preserve the identity with this.
Great, but
usually this is what we do usually. Deformation is much better than to reconstruct.
Okay, but then do you? In the future, would you like to combine your outputs with texture information so that it can be used in virtual reality, maybe?
The texture?
Texture.
Yeah, this is one my colleague would like to do this, but I am not expert in texture. This is why I focus more on geometry.
Geometry. Okay.
Geometry. But if there are some collaboration with you on texture,
sure. Yeah, let's
happy to collaborate with you. I'm not, texture is not my. I don't focus on texture, but it would be nice to have a 3D face, but to have texture. Yeah, I agree with you. This is something that but I'm more focusing on geometry than texture.
Okay. Thank you so much.
Hi. Yeah, thanks for the talk. Excellent. I really enjoyed it. I noticed you wanted to stick mainly with explicit representations of meshes. Like you've got a mesh, you've got point net and then spiral net and things like that for your 3D surfaces. There's been a lot of work recently on implicit representations of surfaces. Sign distance to surface and that kind of thing, which doesn't tie you to a particular mesh resolution, for example. So when you're starting out trying to get involved with these problems, probably one of the first things you're thinking is, shall I go down the explicit mesh representation route or the implicit? And I just wondered what your thoughts were on that.
Yes, I'm not. I read so many papers on this because maybe I don't know. Maybe for implicit representation, you mean like nerve, something like this? Yeah, for example. I understand. Now I agree with you that maybe it could be another direction, but here we focus more on. For me, it's in my opinion, this method is more for a reconstruction of 3D. Here we have a surface. We have a surface, 3D surface. What do we mean by which kind of representation for surface we're using implicit? Do you have some idea about this?
Sign distance.
I agree. That maybe be possible to maybe use some. I have no idea about how can we, Maybe also I don't know, but I agree with you that something that. Well, in my group we think about it, but we don't. Yes. This is good. This is good. Thank you.
Do we have any other questions? Oh, over here, Jeff.
Hi, great talk. I wanted to just kind of follow up on what Albert was asking about two things. One was the sort of head pose and being able to vary that. What do you see as the challenge in being able to allow the head to change pose? And then change pose. For instance, head nod, because it seems like with your mesh you could do that, and yet I think you don't vary that pose.
What do you mean? You mean which kind of the pose of human bodies?
Right. The pose of the head.
The pose of the head.
So head nod or head turn.
Yeah. This is what I say to.
Yeah. No, I was wondering
Yes, this is. We would like to, to extend this work and to take into the head pose, but I have no idea about how can we, adapt this, because we have to take into rotation. I don't know. This is something that we're thinking about it.
Okay.
Yeah, this is good direction.
Yeah.
Yeah.
Okay.
But it's very important because in many cases we need this.
Right.
Yeah, and we need also, we don't take into account, the change of, the A's.
Yeah.
Yeah, this is something that there are many things that we have to do,
Yeah.
I agree with you.
And what about kind of bringing in analysis as well? So so capturing motion parameters from actual person and translating that or transferring those to your mesh.
Yes.
Is that something that you've explored?
To transfer what? To transfer.
So you have an actual person.
Yes. Actual person.
And you want to create a mirror. Of them.
For example, in 3D phase, we have the transfer expression from one 3D phase to another one.
Yeah.
This is very good question. This is exactly what we would like to do, as explained. This is our main project is to have like avatar, interaction with, like a mirror. When you smile, you relax on the avatar to something similar to what, and this is we can transfer.
Yeah.
We have this with our apples. And transfer facial expression to one face to another face. This is possible, yeah. Yes, we can, yeah. Okay. So this is something that we can do. Yes. I agree with you. This is very important question. Yeah. Yeah. Thank you, Jeff, for.
Thank you.
Yeah. Thank you.
Great stuff.
And another limitation of this work is there is no in audio, for example, we don't have facial expression. Yeah. So this is another limitation of this work. It's we don't want to count. We have audio. If I am happy in audio, I would like that my expression. We don't have this. We don't have technical. This is another thing that maybe we have to do it now. Working on it to take into account facial expression during the audio with the audio information. Yeah.
Right. Thank you.
You're welcome.
I think we have time for one more question, if there are any others. No? Okay. Thank you, Mohamed.